1, 2, 3. All right. Audio's working and video's working, presumably. Yep. All right. No one is on the chat window, but nobody's watching. And why would anybody watch? It's 7:15 on a Thursday night. All right, so I'm going to do all these problems. 9.23, 9.33, 9.749, 9.22, 9.43, and 10.21, 10.3. We've got two. It's a kind of a double assignment this week. Neither is particularly long, but there's two in it, and so because I want to cover these chapters to get caught up. There's so many things I need to teach you still. Ugh. So that's what we're doing, and chapter 9.23. Let's see. All right, ready to go? Let's go. 9.23 goes like this. So this is from Eric Mazur's Black Book. 9.23. A 55-kilogram acrobat must jump high and land on his brother's shoulders. To accomplish this, he leaps from a crouched position to a height where his center of mass is 1.20 meters above the ground. His center of mass is 44 millimeters above the ground. In the crouch, and 900 millimeters above the ground when his feet leave the ground. Okay, so again, this is a question where we want to keep a mind on conservation of energy, and we're going to use force. So here's the idea. The first clue says that in the end he's landed on his brother's shoulders like that, and in the end his center of mass is a height 1.2 meters above the ground. Okay, and to do that he jumps. So he starts down low, like that. Here's his arms. So his center of mass is super low on this occasion. How low is it? It's 44 millimeters. That's 40 centimeters. That's 0.4 meters above the ground. Pardon me. And then he stands up super quickly. And in standing up super quickly, he stands up so quickly that he ends up moving with some velocity. And this height is 0.9 meters. Okay. So, how do we figure out how much force? What is the average force exerted on him by the ground during the jump? So, before we go any farther, what I just illustrated. The idea that in these circumstances, sometimes it's helpful to draw yourself a little cartoon to help you parse the word problem. So now it becomes a little bit more obvious what they're talking about. You start down in a crouch, then you're standing and moving upwards, and then suddenly you're up on top of your brother. Okay? and they want the average force and the average normal force. Okay. How do we figure that out? Well, excuse me. Still getting in talkie mode. Well, the idea here is usually the force applied over time changes a little bit. And so it's hard to talk about how much precise force is applied at various times. So instead, when you see somebody say, find the average force, what they want is you to assume a constant force was applied. Okay. You assume a constant force is applied. And in doing so, you're going to calculate one single number. This is an approximation, of course, because in reality, the amount of force you apply on the ground changes depending on what your position is as you jump upwards. And it's generally true that the amount of force applied changes. So what we're assuming is that all those changes kind of average out into a constant value. So on the one hand, we are assuming that there's a constant force, or on the other hand, we could say, well, we recognize that the force is changing over time. What is all the average of those forces, as if it were a constant? So how do we figure it out? Well, we talked about a little bit about it in class. There's an idea that work is being done here. And the question is, how much work? And one of the things we noted is that initially the kinetic energy is equal to 0 here, and the gravitational potential energy is equal to, what do we got? How much does this person weigh? 55 kilograms, so it's 0.4, that's h, times 9.81, that's g, and the mass is 55, that's m. So that is equal to 0.5, oh geez, this is in weird, you gotta, mode? Mode 0. My calculator's in some weird. How do they get in these weird things? No, I don't want that. Nope. There we go. All right. 0.5 times 9.81 times 55 is equal to 269.8 joules. Okay, and at the end is gravitational potential energy is equal to 0.5 times 9.81 times, oh no wait, his new height, 1.2 times 9.81 times 55. Kinetic energy is equal to 0 at the end. How can there be a difference in the energies in these two systems? Well, you know, the book, in a later question in this assignment, the book says, hey, there's a figure skater with their hand against a wall, and they're pushing against the wall, and the normal force pushes out, and you calculate the average normal force, kind of like this question. And then the question they ask next is, how much work gets done by the wall? And the answer is 0. And the way you recognize the answer 0 is that the point of contact between the floor, or the wall and the figure skater, or in this case the floor and the person, doesn't move. And so no work is being done. Alternatively put, you can think about it in terms of energy. The wall, or in this case the floor, isn't actually providing the person with any energy. Where is all this energy coming from? It's coming from source energy. It's coming from chemical source energy in the person's body. So the person's using the force from the wall to change source energy into gravitational potential, well, into kinetic energy in this case, and then gravitational potential energy. But the amount of source energy that gets converted into gravity, so the change in GPE plus kinetic energy is just like before, force times the distance it travels. The equation's absolutely the same. So the idea here being that there are two different there's internal energy in the system, and inside the system, energy can change from one type to another type within the system without having to come in from outside by these forces, these internal forces. Forces don't do any work. So in this case, technically the person isn't, the ground isn't giving the person energy the way it might say if you were in an elevator. But these distinctions are, I mean, I'd be pretty happy if you learned to master all of these distinctions, but they are kind of confusing in that all we need to do is calculate the amount of work done. Okay, so in this case, it's the net force times d, distance the center of mass travels, and then that tells you the change in energy. So what's the net force on this guy? Well, you got gravity and you got the normal force. Gravity is minus 9.81 times 55 in the j hat direction, and I don't know what this normal force is. But like I said before, we can calculate the total change in these energies, this way of summing the energy, and you get 647.5 minus 269.8, and that's equal to the net force times the distance traveled. The center of mass goes up by, well, sure, hey, why not just 9 minus 0.4, hey? That's not too tricky. The result is 647.5 minus 269.8, nope, 8, good, divided by 0.5. The net force is 755.4. And you know that this net force is going to be Fg plus Fn. 755.4 is equal to 0.81 times 55. So this is minus 539.6 plus Fn, and then Fn is equal to 755.4. There, that many newtons. So what did we do? In essence, we saw how the total force was changing. The center of mass moved in accordance to some total force pushing on it, and we saw how this affected the total energy of sorts, not including source energy, but these two energies added together. No, the mechanical energy. Sure, that's a concept. So we saw how this net force affected the mechanical energy of the system, and we knew how far the center of mass moved, so we could calculate the net force. And because we know the net force is gravity times the norm plus the normal force, you can add up and you get that normal force. That's the average. Part B says, what is his maximum speed? What is his maximum speed? Okay. I'll explain the answer to this in two ways. The first way is to say, okay, from this moment to this moment, the net force is these two together, right? So from this moment to this moment, he's accelerating upwards, and then from this moment to this moment, his acceleration is downwards towards the ground, right? Because once he leaves the ground, there's only gravity affecting him. You get a negative acceleration. His velocity is upwards, so from this point to this point, his velocity is upward, his acceleration is downwards, so he's slowing down. Whereas from this point to this point, his velocity is upwards, his acceleration is upwards, so from here to here, he's speeding up. So at this moment, he's traveling fastest. There's another way to talk about it, though, and that's to go, okay, well, let's do a little diagrammy thing. Between 1 and 2, what do the energies look like? Well, there's gravitational potential energy, and there's kinetic energy, and there's source energy. And then between 2 and 3, presumably there's gravitational potential energy and there's kinetic energy, but there's no source energy. You've expended all your source energy. Okay. And we ask ourselves, what are these graphs doing? How are they changing? In the first part, when he's jumping, the source energy is going down, and the kinetic energy and gravitational potential energies are going up. And in the second part, so at this point, the source energy is completely depleted. And afterwards, he's going upwards, so the gravitational potential energy is increasing, and the kinetic energy is decreasing. So this period of time, when he's still jumping, his kinetic energy is increasing, and afterwards his kinetic energy is decreasing. So at this moment, it's the max kinetic energy. So let's figure out how much kinetic energy that is. Well, here's the thing. You know that work is only being done over this period of time, right? You know that source energy is only being consumed in this period of time. So from here to here, the mechanical energy is conserved. From 2 to 3, total mechanical energy is constant. So what are you going to do? The deal is that the E total must be 647.5. And so at time 2, 647.5. Oh, you're missing the bottom. At time 2, the total energy is going to be part gravitational potential energy, GPE, and part kinetic energy, KE. I'll write out those values. The gravitational potential energy is the mass times 9.81 times the height. And the kinetic energy is 1/2 the mass times v squared. We can solve this for v. So 55 times 9.81 times 0.9, 647.5 minus answer times 2 divided by 55, square root answer 2.43 meters per second. That's how we do that question. I wonder if anybody's watching it. Oh, 3 people are watching. Good work. Anybody say in the chat? Thanks for making Donald Trump. Fuck you, Donald Trump. Get off my feed. You're not even Canadian. Those of you watching after the time, Donald Trump, the current waiting president of the United States, is watching me do physics questions. This is an incredible disappointment because he's got better things to do than to watch me do physics. But I guess that's what happens sometimes when you're on the internet and it's a public feed. Even Donald Trump can watch you do physics. All right, so that was it for this question. Let's move on to the next one. All right, let's see how this looks. Can I use the backs of these pages? Yeah, that looks pretty good. Next question, 9.33. 9.33. 9.33 goes like this. A 1,000 kilogram car traveling at 5 meters per second runs into the side of an underpass. Oh, jeez. The concrete wall is not affected, but the car crumples such that in the time interval from the instant of impact to the instant which the car comes to a rest, its center of mass travels forward half a meter. What are A, the magnitude of the effective force exerting it on the car, B, the work done by the wall on the car, and C, the change in kinetic energy of the car's center of mass? All right. So pay close attention to this one. Let's start. So again, we're talking about the average force, which is shorthand for assume it's a constant. There is literally only one force acting. Okay, well, I guess we gotta draw the car. Here's the car. Here's the wall. There's one force acting to the left. Okay, so the magnitude of the force exerted on the car. Well, okay. So the idea is that the center of mass of the car moves forward as the car crumples up. And I don't feel too bad describing a car crumpling up in this case because it probably saved the people inside's lives, as we talked about last time. So the car moves forward half a meter. Okay. And that means that some work got done. Well, kind of. All right. Well, close enough. So we could say that the normal force does work on the. Oh, this is one of these questions where the answer in the textbook, so the answer that Mastering Physics is going to give you, is 0. How should I put it? Forces mediate changing one type of energy into another type of energy. And these normal forces, these ones where the object you're pushing against isn't moving, they tend not to do any work. But anyway, what we're going to do is this. We're just going to find the change in kinetic energy. There's no potential energy in this system because none of it is reclaimable. I'll talk about what the energy does in a second. First, let's figure out what this constant force is. Because the change in kinetic energy is going to be the force times the distance traveled. Okay? So the initial kinetic energy, final minus KE initial. The final kinetic energy is 0. And the initial kinetic energy is 1/2 times 1,000 times 5 squared. Which is minus 12500 joules. And I don't know what the average force is, but I do know it's in the opposite direction, and I do know D. So this force is going to be 12500 divided by 0.5. Yeah, well, okay, hold on. This minus sign that I added, I kind of did it by hand. The idea is we want to know the direction of the force as well. So you just say, force, I don't know which direction it is. I'm going to leave it as a variable. The D vector is in the positive direction. This is definitely a negative number. So this picks up a negative sign, indicating it's in pushes to the left. All right, newtons. Okay, so that was a fun question. Part B. Part B, the work done on the wall by the wall on the car, and 0. See, change in kinetic energy, that's going to be minus 12500 joules. Okay, so let's talk about why this is 0. Because I've mentioned it before, but it's come up a second time, and it comes up on your assignments as well. So I'll explain. Forces change energy from one type to another, or move energy into and out of a system. Okay, so broadly speaking, a system can have kinetic energy, potential energy, can have source energy, and can have thermal energy. Okay. And you add these up at any time, and you get the total energy. Okay? So, the only way for this total energy to change is if a force from the outside of the system does work on it. And work only happens if the point of contact between the force and the system moves, right? We talked about this in class. You push an object, if it moves in the direction you're pushing, you're giving it energy. If it moves in the direction opposite you're pushing, it'll take energy away from it. But what's going on in this case is essentially there's more forces. So this applies to external forces acting on the system. External forces on the system can do work on the system, changing the total amount of energy, right? But systems are often made up of more than one object. You can have two objects attached together with springs, say, and there's lots of forces. So one question is, what about all the other forces on the system, all the internal forces? Internal forces you can multiply the force by how its point of contact moves and do that all day. It's fine. But that's not going to change the overall energy of the system. And the reason for that is equal and opposite forces. Every time two parts of the system push on each other, each one feels an equal and opposite amount of force, and that part is going to move the same way. And so this force will do positive number, this force will do negative number, fine, right? They'll cancel out. Internal forces don't do any work, don't change the total thing. But that doesn't mean they don't have any effect on the energy of the system. What internal forces do is they change energy from one type inside the system to another. Okay? So you imagine throwing a ball up. If the system is the ball and the earth, then if you throw the ball up in the air, the force of gravity changes kinetic energy into potential energy. The kinetic energy goes down as the ball goes higher, and the potential energy goes up, and that's the effect of gravity. Okay. So what's happening in this example? The point of contact between the wall and the car is right here, and it's not moving. So this external force, the normal force of the wall, isn't doing any work. Another way to put it is this wall isn't giving or taking energy out of the system. So where's the energy all going? Because the kinetic energy is definitely going away. The other thing to note is to figure out the amount that the energy of one type of energy is changed into another type. It's essentially the work formula, right? It's just like, all right, so you multiply gravity by the change in height. That tells you the amount of potential energy that's changed into kinetic energy or whatever. Okay, back to this. Where does the energy go? Essentially, this wall pushes on the car, but then the parts of the car push on each other. And as the car crumples up, those points of contact move around. Okay? So what we're talking about is internal forces. And it's internal forces in the system responding to the car crumpling up, in accordance, causing the car to crumple up. It's internal forces. And so these internal forces are going to, in this case, reduce the kinetic energy and increase the thermal energy. Does that make any sense? I hope it does. Some of the other assignment questions ask this, so it's important to keep it straight so that you don't get super confused about why they're asking these questions and why the answer is 0. That said, I play a little bit fast and loose with these distinctions. They don't, physics-wise, they don't show up all that much. It's important to keep straight because it's true. But, yeah. All right, question 14. All right, well, let's see if there's any questions about this. No. Hi, Joseph Lee. Joseph Lee is watching the chat. So it's Joseph Lee and Donald Trump and someone else. Okay. 4.9. Sorry, 9.49. Let's see. That question says, in pushing a dart into a toy dart gun, you have to exert an increasing force that tops out at 6 newtons when the spring is compressed to a maximum value of 0.12 meters. Oh, fun. Okay. So how do darts guns work? It probably says this in the text. But if you don't know, because maybe your parents were pacifists who didn't want you playing with awesome toy guns that are disappointments anyway once you get your hands on them. This is how essentially a toy gun works. There is a little triggering mechanism attached to a trigger. Fine. And then here's the suction cup. I guess people play with Nerf things now. Nerfs don't have suction cups on them. But the idea is you push the dart in, and then once it's in all the way, it clicks on a trigger, and then the trigger holds it in place. Okay? So you push the thing back. You're compressing the spring. You're giving it potential energy. Okay? And then when you release the trigger, that releases the spring, and the spring springs forward, and all that potential energy turns into kinetic energy in the dart. So let's do some stuff. The one clue we have is that we've compressed the spring initial length is, I don't know what it is, but we've compressed it past its initial length to a new length that is 0.12 meters. And we know that the force exerted by the spring is equal to 6 newtons. Okay? So, how much kinetic energy is there? Oh, potential energy. Wait, to answer this question, there's a formula. K x squared, right? Where this x squared is going to be 0.12 meters. But I don't know what this value of k is. Question mark, question mark, question mark. So to figure that out, I have to use this one clue they've been giving me. Luckily, I know that the force exerted by a spring is going to be minus k x. And the force exerted is going to be 6 newtons. Now in this diagram, I've compressed the spring. X, the current end of the spring is to the left of the original point, x equals 0. So it's k minus 0.112 is equal to 6. Value of k is equal to 6 divided by 0.12, 50 newtons per meter. Okay, now the potential energy, 50 times 0.12 all squared. This is a pretty fun question. I wonder if I could ask it for the final exam. 0.36 joules, which isn't very many joules. You certainly couldn't put this on an engagement ring. It's funny that they measure energy in joules, but then they measure joules in carats. They should measure carats in centimeters, and then there's probably a centimeters to energy conversion in there somewhere. They say time is money, but joules are energy. Okay, so what's the launch speed of the dart? Well, conservation of energy. After you launch, so total energy before has kinetic energy and potential energy, and the final energy is kinetic and potential. Initially, kinetic energy is 0 and potential is 0.36, and afterwards, I don't know what the kinetic energy is, mv squared, but I know that once it releases, the potential energy is 0. The mass here is 0.024 kilograms, and so I can use this formula to calculate V. 0.36 times 2 divided by 0.024, square root of 30 is all right, question B. I like this question. If I was lazier and probably a much higher quality instructor, I would probably give you final exams out of this textbook because these questions are fantastic. Does your answer change if the dart is fired vertically? The answer is yes. The answer changes if it's fired vertically. I don't want to tell you I don't want to calculate the answer, but I'm going to give you the reasons why. And it's because when you fire it vertically, here's your gun. Cool, such a cool gun. Spring is squished, and then there's your dart. Fine. And then after you pull the trigger, things like that. Okay. Can you guess why the answer is no? I'll give you another couple seconds. Why is the answer that it will be different if you fire the gun vertically? Time's up. Okay. Initially, energy, final energy. If you go vertically, KE U spring UGPE. If you're doing it vertically, there's also gravitational potential energy in the mix. So at first, these are both 0, Yeah, well, you can set the gravitational potential energy to be 0 wherever you want. It's a relative thing anyway. So the spring potential energy is going to be 0.36. And then at the top, when you've launched the thing, the spring energy is 0. But both of these have changed, okay? So in the first part, in this one, the kinetic energy got all of that delicious potential energy. In this example, the kinetic energy and the gravitational potential energy have to share this potential energy. So it gets divided up between them. Not evenly. It depends on how high the thing goes, and we could calculate that. But the argument is that this number increases. So this number will also increase. It'll go from being 0 to being some other number. But this number is going to be smaller than it was over here. Does that make sense? All right. Well, all right. I'll leave this on to look at. You can look at the sweet gun pictures I drew. Oh, no, there's only 2 people watching the stream. I guess Donald Trump left. Okay, next story is 9.22. Oh, fun. It's a skid question. So, I'll read the question, and then I'll draw a little picture, and then we'll talk about the physics. At the end of a delivery ramp, a skid pad exerts a constant force on a delivery package so that the package comes to a rest at a distance d. The ramp is changed so the same package arrives at the skid pad at a higher speed, and the stopping distance is 2d. What happens to the time interval required for the package to stop? Is this literally the same as 221? End of delivery ramp, skid pad exerts a constant force on a package. The package comes to a rest in a distance d. Oh, I see. Okay, no, this is a different one than question 21. Okay, so before, here's the idea. There's a ramp, you know, it's got old nails in it and stuff, and suitcases would slide down it, and they'd reach the bottom, and then there was a pad. Covered in carpet or something, I don't know, whatever. Okay? So the idea is these things would slide down, and then they'd have some initial velocity, and then they'd slow to a stop, v final, after some distance, d. Okay? So, and that takes a certain amount of time, delta t. I don't know anything about the time, but it takes a certain amount of time. After, you go in and you talk to the management, and the management says, hey, we need to hire a consultant. So why do we need to hire a consultant? But the consultant comes in and says, hey, your ramp is covered in nails and stuff. People don't like how damaged all these suitcases are getting. So the consultant pulls out all the nails and stuff in the ramp. And the result is that these boxes and stuff are traveling much faster. The initial crazy fast. And so it takes a much longer time for them to stop. Okay. How much longer? Well, this distance here is 2d. I'll call this 2d1 and delta t 2. And so the question here is, what's the relationship between these two? Question mark? I don't know. I don't know. Now, one important detail here is that these are the same suitcase. I don't know. Mr. Wu comes in every week to with his bag on an airplane, and every week the same bag comes down the slide, and he goes, "Oh, finally you fixed the ramp. It's not tearing up this luggage anymore." All right, so that detail is important, but we'll get to why in a second. So how do we analyze this? Here's the idea. The thing starts out with some kinetic energy, okay? So by that I mean at this moment, this bag has this much kinetic energy, and this bag has this much kinetic energy. And if I knew how much kinetic energy they had, at least some representation of how much kinetic energy they had, I could figure out what speed they were traveling, right? And that could help me solve this problem, right? Because I knew if you know what initial speed it's traveling at, and you know how far it takes to decelerate to 0, you can figure out the force on it, and then the acceleration. And if you know what the acceleration is, you can, right? So thinking about kinetic energy at this moment and comparing them is the key to doing this problem. Here's the idea, though. I wrote U. How about if I call it E1, E1, and this one E2, and it's the kinetic energy in both cases. How about KE1, KE2? All right, so here's the idea. This kinetic energy goes from being whatever value is to 0. There's a force doing work on it. It's friction. So friction does work on it, and the kinetic energy gets dissipated by this force of friction. Okay? Because the idea is the kinetic energy goes from this number to 0. Turns into heat. Friction slows it down to a stop. And in the second case, KE2 minus 2d FR. Well, before we go on, we're like, okay, are these two friction forces going to be the same? Yes, they are. They're totally the same number. Why are they the same number? Because it's the same carpet, I guess. The skid pad stays the same. It's only the ramp that's changed between them. So the result is, and these bags are the same bags, so they're going to feel the same normal force, so there's going to be the same kinetic friction. So the idea is these two numbers are the same. This is d, this is 2d. And so you conclude in the first box, case has half the kinetic energy the second case does. Maybe the before case. Okay, well that's neat. How do we answer the question of time? Well, here's an idea. You know that the acceleration the objects feel are going to be the net force divided by the mass, right? And in this case, the acceleration is going to be the force of friction divided by the mass, and it's the same in both cases. Both suitcases feel same acceleration. Okay? And you know that delta T1 times A plus V1 is going to equal 0. And keep in mind A is negative. A is pointing in that direction. Yeah, A vector. Okay. and v2 plus a delta t2. So this question is asking me to compare these two values. And the neat thing is that these values are the same for both of them, but these values are not. Luckily, all right, here, hold on. So then you can go delta t1 is equal to, a is negative, so that's fine. Delta t2 is equal to minus v2 over a. And here's the thing, kinetic energy, come on, write nicely. Kinetic energy is 1/2 mv squared. So v is equal to square root 2ke over m. Okay? Dig it. So this is delta t1 is equal to minus square root 2ke1 over m divided by a. Delta t2 is minus square root 2ke2 m divided by a. Alright, why did I do all this work? I did all this work because I know that there's a relationship between these kinetic energies. I know ke2 is equal to 2ke1. So delta t2 is equal to square root minus 2 over m times square root 2, let's just put it all in the same root, square root 2ke1 all over a, and so this is square root 2 times minus 2ke1 over m divided by a, which is square root 2 delta t1. So this is the relationship between the two. Delta t2 is equal to square root 2 delta t1. That's what I wanted to know. Alright, I'm going to pause the feed for a second. I'll be right back. Alright, and we're back. I think, yeah. Okay, we're resumed. I can resume these things. Oh man, I'm talking super slow tonight. This is 9.22, right? 9.43. Hey Ben, why don't you do one of these 3 bubble problems? 9.43 goes like this. You fire a bullet of inertia. Okay, hold on. I'll draw the diagram. Here's the wall. You got a K, and a block here for M, and then a bullet traveling at V, and it has mass M. Alright, so is it updating the video? I think so. Yeah, it should. I think this is going to work. Yes, this is definitely something I tried before. I don't know why the... Oh, no, it's working. Okay, the video's good. We're good. Okay, time to start. Now that I know we're all on board. Yeah, you shoot a bullet into a block. You fire a bullet of inertia M into a block. This bullet is initially traveling at speed v, and the inertia of the block is 4 times the mass of the bullet. The surface on which the block sits is rough, and the spring has a spring constant K, the bullet becomes embedded in the block. If the spring compresses a maximum distance d, so it hits and the spring comes back to that distance d, what's the magnitude of the frictional force exerted by the surface on the block while the block is moving? How do you answer this question? All right, so here's the idea. The idea here is that friction is removing energy from the system. Delta E. Okay? So, I need to figure out how much the energy of the system has changed. E initial, because the work done by friction is going to be the friction force times the distance traveled, right? They're going to be in opposite directions. But, so I need to know the final energy minus the initial energy. Man, this question is super great. Okay, so what's the final energy? Well, there's two parts to it. There's kinetic energy, and there is spring energy. And initially, there's kinetic energy and spring energy. Okay? F times d. Okay, so at the end, how much kinetic energy does it have? 0. It says it's stopped. How much spring potential energy is there? 1/2 k d squared fd minus yes, this is supposed to be negative because they're pointing in opposite directions. This is dot product. But let's just run with it. I don't know what the initial kinetic energy is. Question mark. That m, I don't know. I'm just writing out the formula. And the spring constant 0. All right. So it's clear that what we have to work with right now is spring potential energy and the amount of energy the system started with. It's not m or v. So the question is, okay, so the mass of the system, once the bullet is lodged in the brick, the total mass is going to be 5m. What velocity is it going to travel at? I'll call it, I don't know, u. What's that value u? Specifically, I want u in terms of v. How do I figure that out? Conservation of momentum. So P initial is mv, and P final is 5m times u. So u is equal to v over 5. All right, let's plug that into this equation. Minus fd 1/2 kd squared minus 1/2 5m v squared over 5 squared. Cancel, cancel. And the result is the force is equal to 1/2 kd minus 1/2 m over d v squared over 5. And there's a minus sign because it's in the left direction. That is how we do it. Yes. That's the magnitude of the force. Oh, it wants the magnitude, so you can ignore this sign. That's the magnitude of the force exerted on the surface while the block is moving. Powerful stuff. Conservation of energy lets us do all sorts of Really fun things. Next. Well, 3 are watching. Oh, nobody said anything. I guess I'm doing a good job tonight. So, let's move on to the 10 point. Let's do these in order. Time to do the chapter 10 questions. I'm going to go 10.21, 10.31, 10.41, 10.43, 10.69, etc. Okay? I'm not sure if that's wise. I think these jump around. I think I go to the end for a question. I think the topics jump around in this, but whatever. It's not the right questions. 10.21. Let's begin. 10.21. A worker places a circular saw on top of a long board that is lying on the floor. She and a coworker lifts the end of the boards and carries it across the construction site, placing it across 2 sawhorses at its destination. Discuss the work done by the normal force and the force of static friction by the board on the saw during this process. So, it seems to me that there's 2 parts to this. They're unhappy because their jobs are carrying saws on boards. Seems like maybe not the safest thing to do, but what do I know about safety? Okay. And the second part. Okay, so this question's fun because a lot of the time we generally say that normal forces don't do work. And generally they don't. Certainly in the last, the 9.0 questions we were doing earlier, like the normal force was often not doing any work when cars crash into it and stuff. That said, if the system is the saw and the earth, the environment is the board. So the only thing that can push on the board, the only thing that can push on the saw is this board. In that case, definitely the point of contact between the saw and the board can change, right? Because in this case, the point of contact goes, I mean, okay, so yeah, it stays in place on the board, but the saw moves up and down, and the board pushes it and keeps moving. The saw moves left or right, and it's the board that's pushing it. So in these cases, unlike the ones we were talking about before, the normal force and the static friction force can and are doing work on the thing. Is it supplying energy to the thing? Yes, it's the thing pushing, providing energy. The source energy comes from the bodies of the workers, of course. That's capitalism. But if the system is just the saw, the energy, the kinetic increasing or decreasing kinetic energy of the saw is provided by the normal force. Okay, so say vertical motion, say. The object goes up and down, goes up and down in a controlled manner, it's the normal force does work. So for instance, when they're raising it up, the normal force is providing the gravitational potential energy. It's providing the kinetic energy for the thing to move. When it's moving downwards, it certainly could be falling a lot faster. It's the normal force that's removing gravitational potential energy, or the normal force that's work done by the normal force that's removing kinetic energy, so that the saw doesn't fly all over the place. In horizontal motion, all right, so Fn. In horizontal motion, it's static friction that's pushing it to the left or right, holding it in place on the board. Right? So yeah, static friction will increase the kinetic energy as they move to the left. It'll decrease the kinetic energy as they slow down once they've reached their destination. That makes sense, right? I don't know how much more I need to say. 10.31. Let's see if anybody is... I wonder if you guys are catching all the squeaks my chair is making. I'm doing an amazing job. Thank you, Ty. Ty has just... cause will suck has just said that I'm doing an amazing job. Thank you very much. I appreciate it. Okay, so 10.31 goes like this. You leave your house and walk east for 1 hour, northeast for 1.5 hours, south for 1 hour, and southwest 2.5, always moving at the same speed because you're being chased by zombies or something. Yeesh. All right, let's track your motion. You go east 1 hour's worth, and then northeast for 1.5 hours worth, and then south. Wait, hold on. Oh, geez, northeast. Come on, give me a break. All right, okay. So, walk east for 1 hour. There you go. Northeast for 1.5 hours. 1.5. I'm trying to get this. 1.5 in right. South for 1 hour. Southwest for 1.5 hours. So, or no, 2.5 hours. So that's 1.5. That's 2.5. Realizing it's going to get dark home, you head directly home. So you're going there, home. How long does it take you to walk directly home if your speed stays the same on every leg of the journey? Right. Well, I guess we gotta let's just use vectors. I'll call this L1, L2, L3, and L4. So L1 is to the right, so it's 1 I hat. L3 is 1 south, so it's -1 j hat. L2 is a little bit more complicated because presumably it's a 45-degree angle. 1.5. Where's Calculon? Here you are. So it's 1.5 times cosine 45. So this is 1.06, 1.06. I'm guessing that those 06s are not significant. So let's call it L2 is 1 I hat, 1 j hat. And L4 is 2.5. That's a 45-degree angle. 2.5, no, 2.5 times cosine 45. No, not 2.5 times cosine 45. 1.7, 1.8, 1.8. I think we're working with 2 sig figs, so let's not get crazy. This is minus 1.8 I hat minus 1.8 j hat. Add them all together. If we add them all together, we'll end up with the final position relative to the initial one. We'll end up with this displacement from here to there. Add all the ones, all the I-hats. That's 1, 2. So that's 0.2 I-hat. Yeah, it's pretty close. It's not a bad drawing, just a little bit to the right. Now all the j-hats. Minus 1 plus 1, 0. Minus 1.8 j-hat. Well, I was right to do math on it. This isn't something you can not do. Okay, so the question is, how far away? In other words, find the length of this. I'll draw this as a vector so that you can see this is the final position. It's 1.8 hours down and 0.2 to the right. And so we can use Pythagoras and go square root 1.2 squared plus 1.8 squared. It's the hypotenuse, right? It's this amount. 1.8 squared plus 0.2. Oh, I love this calculator. It's so good. So this value is 1.8 hours. 1.8 hours away. Hooray! Maybe you shouldn't spend an afternoon walking around in circles, huh? Well, that was that question done. Now, 1.43. I'm doing these in out of order. So, yeah. 10.43. Let's take a second, see if anybody has anything to say on the feed. It's Walchuk. Oh, yeah. I'm sorry, Ty Walchuk. It's my bad. I'm bad at reading people's names. Except for Donald Trump's. That's easy. Ugh. Gross. Alright, ball rolls off the table and lands on the floor. Nice! Where'd my ball go? I don't know. Go look on the floor. The horizontal distance between the position of the ball lands and the edge of the table is 0.5 meters, and the tabletop is 0.8 meters above the floor. Oh, sweet. How long does it take the ball to reach the floor? What's the ball's speed when it leaves the table? Oh my gosh, this question's great. Are you ready for how to do this question? Oh, this is amazing. Alright, so I'm going to start by drawing a picture. Here's the tabletop. Here's the floor. Here's the ball. The ball's final position, or at least where the ball lands. So this distance here is 4.3. That distance there is 0.5 meters, and this distance here is, okay, let's put the origin right there. So what do we know about the ball's motion? Before we go anywhere, we have to answer the question. Before we can answer this question, we have to ask ourselves, what do we know about the ball's motion? The idea here is, okay, in the description it says the ball rolls off the table, okay? In other words, when the ball leaves the table, it has some horizontal velocity, but no vertical velocity. and then it goes. Okay. So, how do we answer this question? The first thing it wants to know is how much time it takes to hit the ground. How can we answer that? Here's the thing. We've talked about it in class. When you're analyzing analyzing projectile motion questions, you can answer and analyze the x motion, the motion along the x-axis, independently of motion along the y-axis. And when I say independently, I mean you can write two separate equations and solve them independently. You solve one at a time. The solution of one is also often going to help you with the solution of the other. So, before I go any further, here's the idea. For constant acceleration, we know it's accelerating constant acceleration in the y-axis. Y0 plus Vy0 t plus t squared. And Vy is equal to Vy0 plus at. Constant acceleration problems. We know the motion along the y-axis involves a constant acceleration. And so what is that equation? 0.8 plus 0 times t plus minus 9.81 over 2 t squared. Okay? And we know it hits, we want to know when it hits the ground. And the nice thing about the ground is we know exactly where its y-coordinate is. Ground. I know it looks like a circle, but it's actually the ground. Minus 9.81 over 2t squared. I can solve this for t. I'm looking forward in about 15 years' time, everybody's going to decide that the way 5-year-olds speak English is the grammatically appropriate one, and so to say find t when it hits the ground, everybody will be like, that's a perfect, well-crafted sentence. All right, so in other words, the value of t here solving this equation will just tell us when the object hits this position, the ground. Okay? So you can do it. I'm just going to do it on my calculator. Let's see, I'll move this over to this side and then bring all the rest to the right hand side. So it's 0.8 times 2 divided by 9.81. Take the square root of that, and it's 0.4 seconds. So it hits the ground in 0.4 seconds. Like I said before, so for part B, it wants to know what its initial Vx was. How on earth do we find that? Well, the idea is that it's constant velocity, constant Vx. The acceleration, it's not accelerating along the x-axis. So x is equal to v, I guess, for constant velocity, position is equal to initial position plus vx times t, right? And the initial position here is 0 because we're saying the origin is right under where the ball left the table. And we know that at 0.4 seconds, the ball is at 0.5. So Vx must be 0.5 divided by 0.4. 1.25 meters per second, which was quite a roll, but I'm sure somebody had fun. So that's the speed when it leaves the table. Next question is 4.1. After all that, I still have to backtrack. Okay, let's double check, make sure nobody's saying anything. Ooh, I only have 23% left on my battery. There's probably enough time. Okay, so stop dilly-dallying. That's the point here. 10.41. A rifle is aimed horizontally at a target 100 meters away. He's sad. Because that episode of King of the Hill. So it's aimed horizontally. So straight horizontal. And here's a target. Remember that King of the Hill episode where Bobby's really good at shooting and it turns out that Hank is bad even though it's unmanly? The rifle's aimed horizontally. The bullet leaves the rifle barrel at 650 meters per second. If the gun is aimed right at the bullseye, by how much does it miss the center? Why would it miss the center? Well, the idea here is that this is actually funny. There's a phenomenon called rifling where the bullet spins. So you ever see the start of those James Bond movies where there's like James Bond walks across the street and there's kind of a swirly circle that follows him around? That's supposed to be a rifle barrel that's aimed at James Bond, and then he turns around and shoots the person holding the rifle barrel and everything turns red. Anyway, it's iconic. The swirly thing around the opening of the rifle barrel, that's called rifling, and it causes the bullet to spin. And what happens is if a bullet spins, it interacts with the air that it's moving through, and it causes it to travel along a straighter line. And so it's a more accurate shot for longer. Presumably that's not what's happening in this example. So what's happening in this example is we're assuming it's traveling along projectile motion. And projectile motion means the just like we said before, the x velocity. I don't know, let's say this is x equals 0, and we'll call this y is equal to 0. Okay. It says that motion along the x velocity is constant velocity. Motion along the x-axis is constant velocity. Motion along the y-axis, in other words, the altitude of the thing, has a constant acceleration. So the initial y velocity is 0 minus 9.81 over 2t squared. Okay. So that's projectile motion in a nutshell. Constant velocity for x, constant acceleration for y. So the deal is it reaches the target at how far away is it? Was it 100 meters away? Yeah. 650 times t. Zero 0.1534 sigfigate seconds. Okay? So at that time, it'll be in position, y is equal to minus 9.81 over 2, 0.154 all squared, 0.154 all squared, there's 9.81 divided by 2, so it's going to be minus 0.116 meters. So it'll be, it's about 12 centimeters below a bull's eye. But anyway, so that's why they rifle bullets. They make them spin coming out of the muzzle and that. Anyway, look it up on any American science television show. Yeah, Americans love their rifling. Something about the revolution. Muskets don't rifle. And so the musket balls couldn't travel as far or as accurately as the American rifle bullets. And so they say that's why they won the revolution. And who am I to doubt them? I wasn't there. I don't even care very much. 69. Nope, sorry. Let's see if anybody has anything to say quickly. 22% left. No, nothing to say. Let's go. 10.69. A force. It writes a force. With 3 newtons and 2 newtons. Oh, thank you. This must be a one of these questions that randomizes in the mastering physics. Is exerted on a particle that undergoes a displacement 2 meters minus 2 meters j hat. Determine the work. Okay, so there's 2 ways to do this. I'm going to show you a trick, but first the long way. So just draw them side by side. What we want to do is figure out the angle between these two, right? We want to find the length of these and the angle between the two. So before I go any further, we know that this one is 1, 2, 3 long and 1, 2 high. So it's going to have hypotenuse 2 squared plus 3 squared. Take the square root of that. And this one is 2 across and 2 down. So it's going to have 2 squared plus 2 squared, square root answer. Okay, so we want to know what this angle is, this big angle. So to do that, I got to find this angle first, and then this angle then, and then I add them together. Okay, so this angle is going to be arctan 2 over arctan, open print, no, arctan, open parentheses 2 over 3. 33.7. And the other one is going to be 45. You can do it on your calculator if you want. I don't want to, but you can. So the total angle theta is equal to 78.7, and then f dot d is going to be the length of f, the length of d, cosine this angle. It's going to be 3.61 times 2.82 times cosine 78.7. 3.61 times 2.82 times cosine 78.7. Boop. So this is 1.995. It's pretty close to 2. There's an alternative way to do it where we multiply the like terms and then add. I'll write it out like this. F dot d is, I'm going to multiply, these are both the I hat ones, so I'm going to multiply x times dx, and then I'm going to add that to fy dy. Okay, so that's 3 times 2 plus 2 times minus 2. 6 minus 4 is equal to 2. Same answer! Yay! So doing it this way is faster. I guess it was my choice to teach it to you this way. They both work. I like this way better. No, hold on. I do it this way. This is the adult way to do the dot product. The book does it this way, and I chose to do it in this class this way because it emphasizes a lot of lessons about, you know, the force and how the component of the force pushing in the direction it's moving is the one that does the work. So this one's a lot more geometric. That said, they give you the same answer. On the final exam, I don't care which one you take. And in fact, one of the questions they ask here is, where is it? 6-9. What's the angle between F and D? F dot D is equal to the length of F times the length of D cosine theta. If you calculate it this way, you know this is 2. You can find the magnitude of each of these lengths easily enough. 2.82 cosine theta. And thus, you rearrange this and you go cosine theta is equal to 2 divided by 3.61 times 2.82, 0.196, and then take the cosine of that, and you get 78.7. Yeah, just like we did up here. It's because these equations work. So, yeah, now you know. The book also explains it. Also, everywhere on the internet, every engineering student with a DocuCam or a webcam is busy trying to get their YouTube hit points up by explaining linear algebra on the internet. Oh, this one's fun. Okay, this next question, it draws a crate. Here's what the crate looks like. There. That's the handle. Okay, so it says, the heavy crate has plastic skid plates on the bottom surface, it's these guys, and a tilted handle. What they mean by tilted handle is it goes up like that. Attached to one side. Which is easier, pushing the crate or pulling it? Assume the force is exerted along the incline of the handle in either case. So what we're saying is we can either push it in this direction or we can pull it in that direction. And the question here is, which one's easier? What do we mean by easier? That's a good question. Obviously, in this case, we're talking about friction. This is the coefficients of friction section. We're talking about friction. Which one is harder to push? Which one is harder to get moving? Which one is harder to keep moving? And both, you know, friction is kind of a complicated thing, but normal force always enters into it, right? If I push it downwards, then the normal force exerted by the floor will have to cancel out the mass and gravity, the weight of the parcel, and the force of me pushing down. So, if I push downwards, the normal force from the floor is going to be bigger, and so will the friction force. On the other hand, if I pull it, that will cancel out some of the weight of this box. And the normal force can be smaller. Remember, the normal force is lazy. It only pushes as hard as it needs to cancel out anything pushing into it, right? So the normal force will be much smaller. And a smaller normal force means less friction. So pulling it is easier. That is only in terms of these physics things. In terms of biomechanics, I think pushing is easier than pulling, because pulling you have to kind of maneuvering your body, and pulling is hard. But in this case, in terms of friction from the crate, from the ground in the crate, pulling will cause a smaller amount of friction. Okay, last one, 10.83. A resort uses a rope to pull a 55 kilogram skier up a 40-degree slope at constant speed 100 meters. For 100 meters. Calculate the tension in the rope if the coefficient of kinetic friction between the snow and the skis is 0.2. How much work does the rope do on the skier? All right. Let's make sure nobody's talking. I've got 14% less on my battery, so I'm going to burn through this calculation. This angle is 20 degrees, 40 degrees. And here is the skier. And here is the rope pulling them up. Constant velocity. What does it mean that they have constant velocity? It means the kinetic energy is not changing. Cool. Cool beans. Okay, so how do we do this question? Calculate the tension in the rope. All right. So constant velocity also means no acceleration. And that means the forces balance. Let's do it. So the system is the mass skier. Yeah, I'll just do the long way. System's a skier. Environment, Earth, the slope, and the rope, and the Pope. Forces. There's a normal force, there's a tension force, and there's a gravity force. Now, the book recommends, and I've recommended too, tilting the reference frame. This is something we did earlier on. You say I hat is that way and J hat is that way. Point I hat in either the direction of motion or the direction of acceleration. And the reason we want to tilt it like that is because if we superimpose these axes on the free body diagram, you see most of the forces are either I or J. So the acceleration is none. If you know what the acceleration is, you know what the net force is. None. What do we know about the individual forces? F, N. F, tension. I don't know how big these forces are, but I know which direction they're pointing, right? So I know that the tension, the normal force is pointing purely in the J hat direction. So I'll call it T. J hat, 0 I hat. No, it's the normal force. I'll call it N. All right, tension force is pure I hat. Tension I hat, 0 J hat. The only thing tricky in this case is gravito. So how do you do it with gravity? You know that this is mass times 9.81. This force magnitude serves as the hypotenuse of triangle. All right, so these are right angles. This is the I hat direction. It's negative I hat direction. This is the J hat direction. It's the negative J hat direction. How do these angles line up with 40 degrees? Well, let's see, this angle here is 40 degrees. So this angle must be 50 degrees. All right, so I can calculate the magnitude of these two components because I know this angle is 50. So it's 55 times 9.81 times cosine 50. And 55 times 9.81 times sine 50. Okay, I can fill these in. In the I hat direction, it's in the negative direction, so it's minus 346.8 I hat. And this is the negative y direction, negative j direction, so it's minus 413.3 j hat. All right, now how do I use this? Fnet is equal to Fn plus Ft plus Fg. It's easier just to sum them up component by component. So 0 is equal to 0 plus t minus 346.8, and 0 is equal to n plus 0 minus 413.3. So t is equal to 346.8 newtons, and n is equal to 413.3 newtons. Oh, I forgot friction. God damn it. Crap. Okay. This isn't wrong. What we did isn't wrong, but the point was friction. So friction is kinetic friction, and it's going this way. Okay? So friction is going to be in the minus I hat direction. I'll call it minus little f I hat. Yeah, minus little f I hat plus 0 j hat. How does this change these sums? This is 0, 0, 0 plus friction. This one stays the same, plus 0, so that's still true. This is minus little f plus little f. So there's a big issue, which is that I don't know how big f is or t, so I can't go anywhere with this particular equation, except that f is equal to mu times n. So it's coefficient of friction. 6%. Okay, coefficient of friction. What is the coefficient of friction? 0.2 times 413.3 is equal to 0.2 times 413.3, 82.7 newtons. So this number is minus 82.7, and so T is equal to 346.8. 429.5 newtons pulling uphill. There we go. Scratch. Oh, I guess I put the T. Well, whatever. Okay, so that's the tension in the rope. Part B, how much work does the rope do on the skier? How much work? It's T times, how far does it go? 100 meters. So it goes 42950 joules. That's a lot of work. Done. All right, I got 5% power, so going to call it a night. Thank you for joining me. Remember to do lots of work. Remember to do lots of practice. And good luck on your next assignment. Talk to you later.